the hidden logic behind 1 and 0. Have you ever stopped and wondered how a computer can do something so unbelievably complex using only two symbols, 1 and 0? Right now, somewhere inside your phone, your laptop, your TV, your car, and even the servers running the internet, billions upon billions of tiny electrical decisions are being made every second. And all of them, no matter how advanced the machine looks on the outside, come down to one simple question. Is there a signal or not? On or off? 1 or 0? That is the secret. And the more unbelievable part is this. Everything you see in the digital world, every video, every game, every email, every photo, every website, every spreadsheet, every song, every animation, every artificial intelligence system starts with that tiny pair of opposites, 1 and 0. Two small symbols somehow became the foundation of the modern world. But why those two numbers? Why not 1 through 10? Why not letters? Why not some more advanced code? Why would humanity build the digital age on something that seems so limited? The answer is a story of electricity, logic, mathematics, engineering, reliability, and one of the smartest simplifications in human history. Because computers are not powerful because they think like humans. They are powerful because they don't. They reduce everything into something much simpler, something stable, something machines can handle at incredible speed. In this video, we are going to uncover why computers use 1 and 0, how electricity became language, how tiny switches became logic, how binary became the backbone of every digital system, and why this simple idea turned out to be one of the most powerful inventions ever created. And once you understand it, you will never look at a computer the same way again. Let's begin. Long before computers existed, humans already understood numbers in many different ways. Most of us grow up using the decimal system, also called base 10. That means we count with 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. When we run out of digits, we move to the next place value, 10, 11, 12, and so on. It feels natural to us, probably because humans have 10 fingers. But nature does not care about what feels natural to us. Machines care about what is easiest to detect, easiest to control, and hardest to confuse. And that is where computers begin to separate from human habits. A computer is, at its core, an electronic machine. It works using tiny flows of electricity. Inside its circuits, electrical signals move through microscopic pathways. Now imagine trying to build a reliable machine that must distinguish between 10 different voltage levels, one level for 0, another for 1, another for 2, all the way to 9. That sounds possible in theory. But in the real world, electricity is messy. Signals weaken. Heat changes behavior. Components vary slightly. Noise interferes. Tiny errors can appear. And when your system depends on telling apart many narrow ranges of voltage, those small imperfections become huge problems. But if you only need 2 states, life becomes much easier. High voltage or low voltage, signal or no signal, on or off, 1 or 0. That is the genius of binary. Binary is a number system based on only 2 digits, 0 and 1. Instead of powers of 10, it uses powers of 2. So each position in a binary number represents 1, 2, 4, 8, 16, 32, 64, and so on. For example, the binary number 101 means 1 times 4 plus 0 times 2 plus 1 times 1, which equals 5 in decimal. At first, binary can look strange to humans, but to machines, binary is a dream. Why? Because it matches the physical world of electronics. A switch can be open or closed. A transistor can block or allow current. A memory cell can hold charge or not hold charge. A magnetic surface can point one way or the other. A light detector can see light or darkness. Again and again, the physical world offers machines a simple pair of opposites. That is why 1 and 0 are not just symbols. They represent physical states. In many systems, A1 means on, and a 0 means off. In others, the meaning may be reversed or represented through voltage thresholds. But the principle remains the same. Two clearly distinguishable conditions. This made binary incredibly robust. And robustness matters more than elegance when building machines that must make billions of decisions correctly every second. But the story gets even deeper, because binary alone is not enough to run a computer. The real breakthrough came when engineers realized that these two states could be used not only to represent numbers, but also to represent logic. This idea traces back to a branch of mathematics called Boolean algebra, named after George Boole, a 19th century mathematician. He showed that logical statements, true and false, could be handled mathematically. True or false. Yes or no. 1 or 0. And suddenly, something extraordinary became possible. If electrical circuits could represent two physical states, and logic could also be reduced to two symbolic states, then machines could use electrical circuits to perform logical thinking. Not human thinking with emotions, intuition, or imagination, but formal decision-making. If this is true, then do that. If both conditions are true, continue. If either one is true, allow passage. If not, stop. These became the foundations of logic gates. An AND gate gives an output of 1 only if both inputs are 1. An OR gate gives an output of 1 if either input is 1. A NOT gate flips the signal. 1 becomes 0, and 0 becomes 1. These sound simple. Almost too simple. But when you connect millions or billions of these tiny logical operations together, you get arithmetic, you get memory, you get comparison, you get decision trees, you get software execution, you get graphics, you get sound processing, you get the internet, you get everything a modern computer does. That is the astonishing truth. A computer is not magical. It is a massive machine for manipulating ones and zeros according to rules. And those rules are built from logic. Now here is where people usually ask the next big question. If computers only understand ones and zeros, how can they handle text, pictures, music, and video? The answer is one of the most beautiful ideas in computer science: representation. Computers do not understand a letter the way you do. They do not understand a photo as a memory. They do not understand music as emotion. They only understand patterns. So humans created systems that assign binary patterns to meaning. For text, each letter can be represented by a number, and that number can be written in binary. For example, the letter A can be assigned a numeric value, and the computer stores that value as a sequence of bits. A bit is short for binary digit, meaning a single 1 or 0. 8 bits make a byte, and with enough bytes, you can represent words, sentences, documents, and entire books. Images work the same way. A digital image is made of pixels. Each pixel has color information. Those colors are stored as numbers. Those numbers become binary. So the beautiful photograph on your screen is, underneath it all, a giant grid of numerical values encoded in ones and zeros. Sound is also converted into numbers. The air vibrations of a voice or a song are sampled many times per second. Each sample is assigned a numeric value. Those values are stored in binary. When played back, the computer sends those values to speakers, which convert them back into sound waves. Video is simply many images displayed rapidly, often combined with synchronized sound. Again, all of it is encoded as binary. So the computer does not see a movie as a story. It sees a huge organized pattern of bits. And yet, those bits, when processed correctly, become moving worlds. This is why 1 and 0 are so powerful. They are not the final form of information. They are the raw material. Like atoms forming molecules, bits combine into bytes. Bytes combine into structures, and structures combine into the digital experiences we use every day. But there is another major reason binary won: hardware simplicity. Early computers were huge, expensive, and fragile. Engineers needed a system that could be built physically with the technology of the time. Binary made this possible. When transistors replaced vacuum tubes and computing began to shrink, binary became even more important. A transistor is, in essence, a switch. It can be used to control electrical flow in a very reliable way. Because transistors naturally fit the idea of two states, they became the perfect building blocks for binary computing. And modern processors contain billions of transistors. That means every second, inside a single chip, countless microscopic switches are turning on and off in coordinated patterns. Those patterns perform calculations, move data, compare values, and execute instructions. The reason your computer starts an app, loads a web page, or plays a video is because its hardware is switching between 1 and 0 at staggering speed. This is also why computer instructions themselves are binary. At the lowest level, the processor reads machine code, patterns of bits that correspond to specific operations. One pattern may mean add these values. Another may mean move this data. Another may mean jump to another instruction if the result is 0. Human programmers usually do not write raw binary because that would be exhausting and error-prone. Instead, they use programming languages like Python, Java, C++, or JavaScript. Those languages are translated step by step into lower-level instructions until eventually the processor receives binary machine code. So even the most advanced software you have ever used ultimately becomes ones and zeros. That includes operating systems. That includes search engines. That includes video games. That includes artificial intelligence. Everything digital eventually descends into binary. Now, here is something important. Computers do not use binary because it is the only possible system. They use it because it is the most practical. There have been experiments with ternary computing, which uses 3 states instead of 2. In theory, some multi-state systems can be efficient. But in practice, binary proved easier to build, easier to stabilize, easier to scale, and easier to protect against errors. When a signal only needs to be recognized as low or high, the system has more tolerance. Small fluctuations are less likely to be misunderstood. That is essential in electronics, where perfect conditions do not exist. Binary is not famous because it is fancy. Binary is famous because it works. And sometimes the simplest tool becomes the most revolutionary. Think about it. Human civilization built language from a few sounds. We built music from a limited set of notes, We built all written mathematics from a handful of symbols. And we built the digital age from two states, 1 and 0. Now let's talk about memory, because this is where the idea becomes even more real. When a computer stores information in memory, it stores bits. Depending on the technology, these bits may be represented by electrical charge, magnetic orientation, or other physical conditions. In RAM, tiny circuits hold temporary states. In storage devices, information may be preserved magnetically, electrically, or through flash memory cells. But no matter what the storage medium is, the information still comes down to distinguishable states that encode binary values. That means when you save a file, what you are really saving is an enormous arrangement of ones and zeros. Your family photos? Binary. Your tax documents? Binary. Your favorite song? Binary. Your movie collection? Binary. Your passwords, your messages, your browser tabs, your game saves, your digital art, your spreadsheets, your code, your cloud backups, everything becomes bits. This may sound cold at first, almost mechanical, but in a strange way, it is also beautiful. Because it means the digital world is unified. The computer does not need one kind of machine for text, another for music, another for video, and another for math. It uses one fundamental language for all of them. That common language is binary. And because everything shares that foundation, computers can combine different forms of media seamlessly. A website can include text, images, animation, sound, user input, and live calculations all in one place because underneath it all, the machine processes the same basic kind of signal. That is why your phone can be a camera, a calculator, a map, a music player, a television, a notebook, and a communication device all at once. Binary makes digital universality possible. And yet, perhaps the most mind-blowing part is this. Computers do not know what 1 and 0 mean in the human sense. Meaning is something we assign. To the machine, these are just states being manipulated according to rules. The meaning appears when humans design systems around those states. So in one sense, the computer is unbelievably simple. In another sense, it is unbelievably powerful. That combination is the secret of digital technology. Extreme simplicity at the bottom, extreme complexity at the top, and one grows out of the other. That is the architecture of modern computing. So why are 1 and 0 used to run a computer? Because electronic systems need reliability. Because two states are easier to detect than many. Because switches naturally fit on and off behavior. Because logic can be represented as true and false. Because hardware built on binary is practical, stable, and scalable. Because all kinds of information can be translated into patterns of bits. And because once humanity found a simple language machines could handle, we used it to build an entire digital civilization. Every email you send, every file you open, every video you watch, every game you play, every search you type, every AI tool you use. At the deepest level, all of it is a storm of tiny switches, quietly flipping between 1 and 0. And that is what makes the idea so incredible. The digital world does not stand on a mountain of complexity. It stands on a tiny decision repeated endlessly. Yes or no. On or off. 1 or 0. So the next time you open your laptop or tap your phone screen, remember this. Behind the glass, beneath the icons, under the apps, below the colors and sounds and speed, there is a hidden language silently doing all the work. A language with only two symbols. A language so simple, it almost seems impossible, and yet powerful enough to run the modern world. that is the story of why computers use 1 and 0. Not because machines are limited, but because simplicity, when harnessed correctly, becomes extraordinary. And from that simplicity, everything digital was born.